Greetings and welcome to another video. In this one, I'm going to talk a little bit about the logic behind a tree. The previous video on trees was more about their general functionality and how we're going to be using them with the project. This one's delving a little bit more into the actual pseudocode on how the trees are actually going to function. And in case of the computer scientists reviewing this, I apologize in advance for utterly butchering state diagrams, but hey, it works for demonstration purposes. All right. There's three primary things that I want to cover for the logic on trees: node creation, navigation, and splitting. These are the three primary things that I want to take a look at in terms of the logic. Let's take a look at node creation first here. There's really not much that goes on in node creation. The biggest thing, at least for the project that has been assigned to my students, is this ID field. We want to keep track of the ID of every single node. Now this becomes useful in our BSP splitting algorithm because when we start having problems, we can use these node IDs to narrow down where the problems occur and use the debugger to set breakpoints so that we will only break into our algorithm when we hit the problem node IDs. So it's one of the main reasons why we want to do these node IDs is so that, and it help us with our debugging. And also, this is assuming that we are inside the creator. So we're the constructor, sorry. This is assuming we're inside the constructor for the node class. So a new instance of a node has been created. First thing we need to do is we need to assign the current static ID value to the ID value for this particular node. Keep in mind, those are two separate variables. The node class itself would have a static global ID or static current ID value, whatever you want to call it. And then you would have a private integer value called myID or maybe just ID, which has that particular node's ID values. You can have two different ID variables. A static ID variable, like I said, maybe called global ID or current ID, and a per instance variable, a non-static, that will track the ID for that specific node. So we need to assign the static to the self ID, and then we need to make sure that we increment the static ID so that way the next node that comes along and gets created gets a correct ID value. We don't want multiple nodes with the same ID value. I also want to take a moment to point out right here that because of this sequence of events, creating nodes is not thread safe. And what does that mean? Well, when you multi-thread or do concurrency, having two tasks running at the same time, you use this concept called thread. A thread is a line of execution that a CPU is working on. And you pretty much almost can't find a CPU nowadays that is single core. I mean, I think most phones even nowadays are dual core machines. So multi-threading is where you get all your performance from. And so you've got to always be aware of when you're doing things that are thread safe and when you're doing things that are not thread safe. This is not thread safe. If you have two separate threads running simultaneously, each of them creating nodes, you will run into problems with this. So just be aware of that. We're not going to try and fix that. You just need to be aware that, hey, this is not thread safe when you're creating the nodes. All right, so that's enough about the ID. Moving on. You want to verify that however you are handling your references to your children, that, first of all, you don't have typos, and secondly, that you don't have, that both of your children are, come on, I'm sorry, I cannot stand typos when I catch them. Okay, you need to make sure that both of your children are null, because when a node is first created, it should not have any children. So you need to make sure that your children nodes are both set to null. Now, the parent is an interesting design question. There's two approaches you can take to the parent. One is to make the parent a public variable, and just automatically set the parent to null and let whoever is creating this instance of the node worry about properly setting the parent. A perhaps more strictly correct way of doing it with object-oriented principles would be to set up the constructor such that you must pass in a reference to a node to be used as the parent. Even if that reference is null, remember, you can pass in null as a parameter. And so the constructor would force the user who is creating this node in code to pass in either a reference to a node or null. So that way the parent is always assigned. That is a critical portion there of creating a node, making sure that the parent's either null if you're the root, or that it has an actual proper reference to its parent. And then that would end the node creation. Like I said, node creation's pretty simple. Now let's go ahead and take a look at splitting a node. Splitting a node's pretty simple again. It's pretty straightforward, but you got to make sure that you're thinking about setting everything, because if you miss setting something, it can seriously mess up your tree. So we've got this mythical split node method. Now the specific split node method probably should be in the node class, because it's the node itself that is causing it to split. The actual mechanics of splitting should not be handled in the tree. This is a node operation here. Now the tree is going to be the one calling the splitting. When you tell the tree, okay, let's grow the tree another level, the tree is going to have to go find all the leaves and tell all the leaves to split. But the nodes themselves is where the splitting code should reside. So we're going to create two new node instances, node 1, node 2. And we need to make sure that parent is set. Whether we're actually saying node1.parent equals this, in the case of C# code, which we're using, or if we're using the constructor method, and when we create the nodes, we pass in a reference to the node we're in. So, node 1 equals node, new node, and then pass in a reference to this. So, we got to make sure that our parent is set. Next, we need to make sure that our children are set. So, again, within the node that we are currently in, this dot child 1 is going to be equal to node 1. This dot child 2 is going to be equal to node 2. Now, the order in which you do this is very important. This actually has a critical impact on the binary split algorithm. What your assumption is here as to what you assign to child 1 and what you assign to child 2. Doesn't matter for the tree project, for the tree data structure project, but once we get into the algorithm, it is going to matter. But we'll deal with that later. Now, an optional thing, this is purely optional. You can stop it here, in the split, you're done. Now, you could optionally continue on to update a leaf list, because we're going to need that information. When we grow the tree, we're going to need to know where all of our leaves are. And when we do certain operations with the BSP algorithm, we're going to need to know where all of our leaves are. So maintaining a leaf list can be very useful. And so this would be the point here that you would add your node 1 and node 2 to this new leaf list that you are building, because they are now leaves. They're the new leaves. They don't have children. All right, so that's splitting it. Navigation's a little bit trickier. There's two primary ways of navigating through a tree structure. One is a depth-first traversal. The other is a breadth-first traversal. What that is the depth first causes you to go all the way down the tree, and then until you get to a point where you hit a leaf, and then you go back up and down and back up and down. And actually, that might be a little bit easier to see with a picture, so give me a moment. And ta-da, instant treed picture. So a depth first traversal says we start at the root, then we're going to go down a child, and then we're going to go down, and we can't go down anymore, so we'll officially visit here now. We'll go back up to here. We can still visit this child, so we can't go any further here. We'll officially visit here. Both of our children have been visited, so we'll officially visit here. We'll now go back up. We can visit this child. We can visit this child. Can't visit anything else. Officially visit here. Go up. Visit this one. Officially visit here. Go up. visit here, go up, visit here. That is a depth-first traversal. And when you're dealing with a balanced binary tree, that generally makes the most sense. A breadth-first traversal says you visit here, then you visit here, then you visit here. And that's a breadth-first traversal. So we're going to stick to the depth-first traversal. A potential use for this is if you are not maintaining a leaf list, you will need to do a full traversal of your tree in order to find all of your leaves. And how you do this is recursion. This is going to be a recursive function. This is going to be the navigate function. And navigate is a tree level function. The nodes themselves aren't really supposed to be talking with one another. Nodes are nodes. They deal with their own business. The tree is the one that handles the navigation. So the tree is going to have a navigate method. Or, in the case of our example of finding leaves, perhaps you'll have a find leaves method. And that will start the process. And so you'll call navigate on the root node. So we'll enter here, and we check our children. So we're going to check our instance of child 1. Now this is where we're going to take advantage of the fact that we have a balanced binary tree. A balanced tree says that if you've got one child, you've got two children. The tree is always fully balanced on the left and right. There's no such thing as missing a right child or missing a left child. You always have two children, if any children at all. It's two or none. So all you need to do is look at the instance of child 1. Is it null? Well, if it's not null, that means we need to continue to navigate. So we're going to call the navigate function again on child 1, and we will call it again on child 2. And so if we follow this trail, we've called navigate on this one. We've checked, our children are not null. I have called navigate on this one. And let me just grab a little junction point here. So we've called navigate. We've called navigate. And now we come down to this node here. We're going to check our instance. Child 1 is null. That means both of them are null. And we can do whatever action we need to do because we now can officially visit this node. In the case of building a leaf list, we would then say, we're at a leaf now, so let's add it in. So now we're going to, and we called navigate on this one. Now, however, since this one is done, we're going to end. So we fall out of that one, and we come back up to this function call. We've done the navigate on child 1. Now we're going to call navigate on child 2. So now we're going to come down here and visit child 2. Child 1 is null, so therefore we can do our action. We can officially visit the node. We then end, so we fall out. We're back up to here. Now we have finished with the recursion part of it. We've called navigate on child 1. We've called navigate on child 2. And again, depending on why you're navigating the tree depends on what you're doing here. If you're doing, like I said, building a leaf list, well, obviously we don't add this node to the leaf list. It's not a leaf. So at this point, we would just simply navigate end. If instead you are deliberately visiting every single node in the tree, you would then officially visit this node at this time and do whatever action it is that you are doing. But we're stepping through as an example of building a leaf list, so we're done. So this one closes out. Now we're back up onto this navigate function call, our original one. So we've done navigate on child 1. Now we're going to call navigate on child 2. And so we're going to be down here. We'll look at this one. Child 1 is not null, so we're going to call navigate on child 1. And so we're on this function call now. Child 1 is null, so we can visit. So we add this node to our leaf list. You can go away. We come back up now to this function call. We've done child 1. Now we need to do child 2. So we call navigate on child 2. This node's children are null, so we perform our action, add it to the list. We then exit out. So this is now done. We now return up to here. We have done both of these calls, and since we're doing a leaf list build, there's nothing else to do, so we end. We come up here. We have now done call navigate on child 2, so we're done with this state. And again, nothing else for us to do, so we end, and we've backed out of the recursion chain. So that's how you do the navigation. Now, there's one more diagram, actually, I just remembered, that we need to take a look at. Growing the tree is another important operation. Now, in this approach, I am assuming that I am always maintaining a list of all of my leaves, and I've got the structure designed accordingly. You do not have to maintain a list of all of your leaves. You can have a method, like in the navigation one that we just went over, whose sole purpose is to navigate through the tree, find all of your leaves, and build a list off of that. So that is a perfectly valid approach. This is just the approach I prefer. Now, the key thing here, when you're growing the tree, is that you've got to maintain the difference between what was your old leaf list and what is your new leaf list. Because if you just simply try to go over your leaf list while you're changing your leaf list, you're going to run into some pretty bad problems. First of all, if you actually use a for each loop to navigate or iterate over a list, it will not allow you to change that in the for each loop, which is a good thing. Nothing's going to stop you, however, from using the index value, using the standard for loop, and changing it while you're in the middle of the for loop. That's not going to be good. And so the first step here is, I say copy, but I'm not really copying. Remember the memory model in C#. Class references, they don't actually copy things when you say equal. So if I say, if I have a list of nodes called leaf list and a list of nodes called old leaf list, and I say old leaf list equals leaf list, I'm not creating a copy. I'm just saying, okay, now both leaf list and old leaf list point to the same location in memory. I haven't actually copied any data over. I'm just saying, okay, you both point to the same location in memory. And so once I do that, I now have, this old list information here. So now I can come along and reset leaf list. Whether I do a list.clear or I actually just, or I do a list equals new list, doesn't matter. The key thing here is that I clear out that old data. Now, that doesn't impact the stuff that's out on the heap. So when I say leaf list equals new list, I'm not actually destroying the memory that's already been allocated out there on the heap. It's still there. And since I have old leaf list pointing towards it, I'm not going to lose it. So I say old list equals list, create a new list, and then I need to iterate over the old leaf list. You don't iterate over the leaf list, you iterate over the old leaf list. You can do this with a for each, you can do it with the standard for loop, doesn't really matter, just as long as you go over every element in the list. And then as we go through all of those nodes in that list, we call split on those nodes, which of course is referring back over here to this logic. And again, on this logic here, I say, okay, well, it's going to add it to the leaf list. Now, this right here tells me that I've got a slight problem, or at least I've got some additional information that I need to make sure is visible. Because growing the tree, this is obviously a tree-level method. Splitting a node is a node-level method. And yet I'm referring to a tree member variable. So I've got to reconcile this. This is also why diagramming stuff out like this is a phenomenally good idea, because it gives you it really helps firm up in your mind what is going on. What are my relationships here? I've got something that, I'm doing something in the tree, but then over here in the node, I'm trying to refer back to something that's only visible in the tree, and how am I going to make this work? And so there's a couple of options to this. You can make sure the nodes know what tree they belong to and make the leaf list a public list. So, a node, whenever you create a node, it automatically, you set up the code such that the node always knows what tree it belongs to and can therefore reference that tree to get to the list. You could pass in the list when you call split. So when you call your node split method, you could pass in the list, which is fairly efficient. Remember, you're passing in a reference to the list. You're not passing in the entire list. So you're basically just passing a pointer along to the split method. So it's fairly efficient. So I could pass in my leaf list to the split, so that way when I do my split, I can update that information. Or after I do the node.split, I won't do that here. I don't want to do that there. And instead, after I do the node split, I would have an extra step here where I say, okay, take cur nodes child 1, take cur nodes child 2, and add that to the list. So it's a really good way of being able to plan out, okay, what are my relations? What do I need to do? All right, enough on that. So we're going to do the node split. And as long as there's items back in the list, we're just going to keep in this iterate loop here, split, 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 until we have split all of our nodes. Okay, so there's no items left in the node, so now we end, and we have a complete list. Now, there's one thing that I haven't covered yet here that's actually quite important, and that is making sure that the tree sets itself up correctly. When you first create a tree, it has to have a node. That root node is also going to be a leaf. And so if you are doing this method, you have to ensure that when you first create a tree, that the root is in the leaf list, because it is a leaf. It's got no children. So you've got to make sure that you do that, otherwise this logic will fail because there's nothing in your leaf list for it to work on. All right, and I think that pretty much covers the logic portion. This UML diagram will be available on Angel. You do need star UML to be able to read it. It is a free program, one of the suggested resources that I had for the class. And so with that, I don't think there's anything else to say on this. And so until the next video.